Okay, so we're nearing the end of this unit, and kind of the last big thing is talking about the second derivative and concavity and points of inflection. Okay, so let's get the definitions and stuff out of the way. Now, for concavity, a curve is called concave up when the slopes of f prime are increasing. Also, what happens concave up? The second derivative, so f double prime, is greater than 0. So if your second derivative is greater than 0, so you can see your slopes, negative, then they go to 0, right, and then they go to positive. Okay, so when you got positive, you got a very happy person. Okay, positive, happy. Just keep that. Okay, slopes are increasing, we're happy. Now, when a curve is concave down, okay, so that's fx prime slopes are decreasing. Okay, so we're positive, a little less positive, 0, negative, and then more negative. That's when f double prime x is less than 0. That is a very sad person. Is it possible for one to be true and the other not? No. No. Okay. Now, another important thing that we're going to do is when it changes from, in this case right here, concave up to concave down. There is a point that that has to obviously change. So if it's positive going to negative, there was a change there. And the only way to change from positive to negative is to have a 0 there. So that is when f double prime x equals 0 or undefined. Okay, so these are points of inflection. So this would be an IP, and here would be an IP, or PI, doesn't matter what you want to say, but usually it's called IP, inflection point. Inflection points. Now, so critical values are inflection points, but it does, this is important, this should say, they do not always mean a change in concavity. So if you had something like this, actually, that's a little bit, so if you went like this and then like that, well, that changes. But what if it went like this? Okay, so this is an inflection point, but it's still concave down here and concave down here. So even though it is an inflection point here, why? Because this is when f double prime x would not exist. Why? Because you can't find the slope at that point. So if the change in concavity occurs at a definite point, then we call this a point of inflection. Okay, so I just want to sum it up to find CVs, which are points of inflection. That's when we want to find when f of x, or f double prime x equal 0. So critical values will be inflection points, critical values, just like in the first derivative. When we find, is it increasing or decreasing, this is when it's an inflection point. Okay? So, just looking at this graph, this would be concave up from here to here, and then about there, it changes from concave up to concave down. This right here would be your inflection point, and that would give a answer of 0. This is where the second derivative would be positive. This is when the second derivative would be negative, right? Okay, then we've got here to here. Actually, why don't I just do all my concave up in red? So here's concave up to about there. And then it changes to concave down. Okay, then we would have a point where, oops, I should have put my inflection point there before I move on. Then we also have another inflection point. Now this is where the second derivative would not be defined. And then goes to concave up. Okay, let's do just a couple examples. So for this graph here, wants us to state the intervals of concavity and points of inflection. So it's not asking for x-intercepts. It's not asking for, I mean, there isn't any asymptotes, but it's not asking for increase, decrease, max, mins, none of that. Just wants inflection points. Okay, so we're going to have to do the first derivative first. So y prime equals, what would it be? 6x squared plus 48x minus 5. Then let's go to the second derivative, which is 12x plus 48. Now, remember how we were trying to get in the habit of always putting y prime or fx prime when that was the first derivative. So now we're going to do a second derivative. So this would be f double prime of x. What we need to do this, just like we needed to do for first derivative, was find any critical values. So y double prime equals, I can take a 12 out of this, and it would be x plus 4. So what's my critical value? Negative 4. So you just put a negative 4 there. Right? And then you do your test values. So if I put in negative 5, 12 times, that would be a negative. And if I put in 0, yeah, I would get a positive. Okay, so it is concave down to here and concave up here. Okay, now it didn't ask us to draw, it just wanted to know, okay, so it's concave up at -4 to infinity. It's concave down, -infinity to 4, -4, sorry. And then it asks for the points of inflection, so that would occur at f of -4. But I've got to take -4, I got to put into my original equation, and I get 255. So the inflection point is -4, 255. Okay, now it didn't ask us, but if we were going to do a rough graph, we have negative. Now, first of all, this is a cubic, right? So how does a cubic go? And it's a positive cubic, so it's going to do something like this. Right? We do have an inflection point at -4, and then say 255 is there. Okay, so I have an inflection point here. Okay, now you can see how this gives us some information about, well, from here, it's concave down, right? Then it switches to concave up. So if I have to start in quadrant 3, I'm going to be down here somewhere, and I don't know, I might just go like this. See, I'm still concave down. And then from this point, I am concave up. Now that's a very rough guess because I do not know my max or mins for those points. But you can see where if I went and found my max and mins, then I would be much better off. And one thing that you'll start to see is if I had an in first derivative, I want you to think about this. First derivative, I have an inflection point right here. Instead of doing intervals of increase and decrease, I could just go to second derivative, because if it's concave down, wouldn't it have to be a maximum and a relative max, right? And these are concave up, and if I had an inflection point here for the first derivative, that would have to be a relative min. Okay, so there's kind of two ways to check if it's a relative max or min. You could do your intervals of increase and decrease, or you could do second derivative at that and go, hey, what between there, what was it? It was concave down. Oh, it must be a relative max. Okay, so this one, we're going to see if we can sketch this entire graph without a graphing calculator. Okay, so even things like domain and range. Domain, what would be the domain of this? X in the reals, right? Range, X in the reals. Now you're going to probably just intuitively check that if you see that it's a rational function. You're like, I'm going to go find asymptotes, right? The other thing you want to do is have a rough idea. You know, it's positive and it's to the fourth, so it's doing something like this. No, it's y. Did you guys pick up the tone of the voice there? Just remember who marks your tests. That's all I want to say. Sometimes people forget that. Okay, so let's do intercepts. Okay, so we'll do y-intercept. That's when x equals 0. So that would be 0. 0 is my y-intercept. X int is when y equals 0. So 0 equals, I'm going to take out an x squared, leaving me with x squared minus 8. So we have 0 is one of them, and plus or minus the square root of 8 would be the other one. Now, because most students couldn't tell you what the square root of 8 is, and it's harder to graph if you don't know that, right? So that would be plus or minus 2.82. Now, I'm sure you're going to figure that out later when it's time to graph, because you're going to be like, I don't know what that is. So I just kind of get it in my mind so I know where I should be putting those points a bit. Okay, so we got, we don't have to do asymptotes, of course, so let's go for max and min. Okay, so we need first derivative. So y prime equals 4x cubed minus 16x. Y prime would be, take out 4x, leave me with x squared minus 4. So y prime equals 4x, and that's the difference of squares, x plus 2, x minus 2. Okay, so we get CVs 0, negative 2, and 2. Okay, so negative 2, 0, and 2. Might as well start with negative 3. Okay, so that would be so if you put it into here, you got a negative. Negative 3 plus 2 is a negative, and negative 3 minus 2 is a negative. So 3 negatives is a negative. Okay, so between negative 2 and 0, let's go negative 1. So I will have a negative. Negative 1 plus 2 is a positive, and then negative 1 minus 2 is a negative, so that will give me a positive. Okay, between 0 and 2, let's pick 1. That gives me a positive. 1 plus 2 is a positive, and then 1 minus 2 is a negative. Okay, so that's a negative there. Okay, and then I'm going to try 3. Oh, I should label this f prime x, right? 3, I will get a positive. I will get a positive and a positive. Okay, so going down, going up, going down, going up. Okay, so you're increasing negative 2 comma 0 union 2 comma infinity. You're decreasing negative infinity comma negative 2 and 0 comma 2. Okay, we need to know there's a local min at negative 2, right? Negative 2 comma something and 2 comma something. Okay, so you make sure you're putting into the original equation, and just to speed things up, I'm going to give you those. That's negative 2, negative 16, and 2, negative 16. Okay, and then what we learned today, let's do our concavity. Right, that's when, oh yeah, sorry, forgot that. Local max is at 0, 0. Okay, second derivative for concavity, right? So what were we? We're at 4x cubed. So let's just write that. Y prime was 4x cubed minus 16x. So y double prime would be 12x squared minus 16. Okay, so let's factor that out. I'm going to take out 4 is the best I'm going to do. 3x squared minus 4. Okay, so when I want to make this equal 0, I'm going to want this to equal 0. So when does 3x squared minus 4 equal 0? 3x squared equals 4. Divide by 3. X squared equals 4/3. And if I take the square root of both sides, I will get x equals plus or minus 2 over root 3. Okay, and what's that? It's about 1.15. So plus or minus 1.15. Okay, since I have to do a interval test, it's nice to know what 2 over root 3 is. So f prime x. Okay, so I got negative 2 over root 3. And over here I will have 2 over root 3. Those are my inflection points, right? Okay, so that's negative 1.15, so I should be able to test negative 2. So 4 times negative 2 squared minus 4, that's all positive. Between these I can put 0. So that's 0 minus 4, so that's negative there. And then positive 2 will again give me a positive value. So happy, sad, happy. Okay, so I would be concave up from negative infinity, comma negative 2 over root 3, union 2 over root 3, comma infinity, and concave down, negative 2 over root 3, comma 2 over root 3. Okay, we're almost ready to graph it, but I do not know when it's changing from positive to negative concavity, but I do know the x value of it, so to find the y value, I've got to put into the original equation. So f of negative 2 over root 3, and I know I did that somewhere. What did I get? Oh yeah, negative 80 over 9. And f of 2 over root 3 equals negative 80 over 9. Okay, so I'll just leave that down here for a bit. So I'm looking at a graph now. Now the important thing is to kind of put as much information on the graph as you possibly can. Okay, x-intercepts or y-intercepts. Those are always good. What are my x-intercepts? We got 0, 0 is one of them. So x-int, I've got plus or minus root 8, which is 2.82, right? So, and negative 2.82, so that's my x-int. And I'm going to put negative root 8 here, so I kind of have some bearings. And positive root 8, that's another x-int. Okay, I got some minimum values at negative 216 and 216. So here's negative 2, and down here would be like negative 16. So I've got a min there. And at 2, negative 16, I have a min. I guess we can write local min. Now there's kind of one thing that does help me out on this one. When you come all the way up here, all the way up here. Well, that was a long question. This is my equation, right? And this does tell me that this is it's a bounce, right? So it's just one piece of information that I forgot to point that out when we were looking through it, but that does help. Okay, now sometimes it's going to look like too much information on here, but what are you going to do? I'm decreasing from negative infinity to negative 2. So I'm decreasing, so you can put decreasing like that. And then I'm increasing from negative 2 to 0. So it'll be like that. And then from 0 to negative 2, it should be decreasing again. And from negative 2 to infinity, I'm increasing. Okay, and then I just want to do these. These are my x-intercepts. And just always keep in mind we're dealing with a W. The next thing is from infinity to negative 2/3, or 2 over root 3. So we haven't even put that on our graph yet. So we have an inflection point at, and that was negative 1.15. So that's about there. That's negative 2 over root 3. And what was my negative 80 over 9 is negative 8.89. So it's about here. This is an inflection point. You can see how lots of colors helps here. And then I've got the same thing on the other side. I've got 2 over root 3 and negative 8.85 is there. Yes, those are both inflection points. And it says that I am concave down from infinity, negative infinity, to 2 over root 3. So I'm concave down here, up, concave up, sorry. See, it pays to be slow. Okay, and then from 2/3, or negative 2 over root 3 to 2 over, we're concave down. Okay, and then we're back to concave up. Okay, so it's important to know that we will start up here and finish here just by doing my initial knowing of its even function, it's positive. So if I'm starting from there, I'll go through my first x-intercept, and I have to be going concave down all the way to here. So draw your graph, make sure you're concave down all the way to your inflection point. Now from there, I'm going to go up, but I have to be going, so, and as you can see, I have been decreasing all the way to this point, and make sure you're increasing all the way here, but you'll be increasing with concave down. And that's why I do this. I put my, see, this says increasing with concave down. So to be increasing with concave down would be like that. This says to be decreasing with concave down. From here to here, it says to be decreasing, but concave up. So decreasing, concave up. From this minimum, it says increasing with concave up. There it is. Good stuff. Okay, that was the room to be able to draw it, but. Okay, so page 230, number 7, we'll just write down the question. You want to sketch the graph of the continuous function with the following conditions. Okay, so the first condition is that f prime of x, the first derivative, is greater than 0 for the interval 0 less than x, greater than x is greater than 0, less than 1, and f prime x is less than 0 for x greater than 1. Okay, so let's see what that means. From 0 to 1, it's greater than 0. It's positive. So that means it's increasing. And from 1 to infinity, it is negative. So it's decreasing. Okay, so what can I infer from this? That there is a, so therefore, a local max at x equals 1. Okay, so anytime you get conditions, I would try and put them on a number line. I mean, for some people, they may think, oh, that's pretty easy, I got to figure it out from there. But if you're a visual person, draw it out. Okay, now what if f double prime x is less than 0 for the interval x is greater than 0, less than 2, and f double prime x is greater than 0 for x is greater than 2. Again, let's draw it out. Okay, so we got 0, I got 2. From 0 to 2, it is less than 0, so not happy. And from 2 on to infinity, I am positive, so I'm happy. So it's safe to say, therefore, an inflection point at x equals 2. Okay, the next condition, it says the limit as x approaches infinity of f of x equals 0. What did that mean again? It's an asymptote, right? So, therefore, horizontal asymptote at y equals 0. Okay, and they also said that f of negative x equals negative f of x for all x. Now, whenever you can substitute negative x in, it comes out as negative f of x. Okay, this is considered an odd function, therefore it's an odd function. So, symmetry about the origin. Odd function. We did notes on that, right? Odd and even functions. So example, if you can put like example, say x cubed. If you can put negative x in there, well, I should say this, f of x equals x. If you can put negative, and so that would be negative x cubed, which is the same thing as negative x cubed. So f of negative x does equal negative f of x. It's an odd function. It's even if you can put negative x in there, and it comes out as f of x again. So x squared would be a good one. If you put negative x in there, it just comes out as the same function. That's an even. Okay? So now with all of this information, we're supposed to be able to draw a graph. Well, that's always a good place to start. Okay, what numbers should we even put down on this? We got any good critical values? We got 0, we got 1, and 2. Okay, what's happening at 1? At local max. What's happening at 2? Okay, so let's also, what's happening, it is increasing from here to here. and it is decreasing everywhere after that. From 0 to 2, we are concave down. And then after that, we're concave up. I also have a asymptote. So I don't know if that's showing up for you guys, but no, it doesn't tell me about any x-intercepts, y-intercepts, anything like that, but so right about, I don't know, I guess it'd have to be around here somewhere is an inflection point, right? So from 0 to 1, I am increasing and concave down. So, whoa. Let's go with that. So it would be increasing and concave down. I still have to keep going, but I'm going to be decreasing now, but still concave down. Okay, I got to keep decreasing, but I got to be concave up. So I don't have to say that across the asymptote. It could, but we don't know that for sure. It didn't give me any. So you could cross, whatever. Now this is the only thing that we haven't talked about yet, and that is taking it and okay, so you'd have your IP here and local min. Okay, you guys have the homework written on the bottom there? Okay, so it's page 229. 1, 2, left column. 3, 2, and 4. And number 4. Ooh, that was a close one.